chat questions. We also have two guest panelists, Aaron Kolb and Paoli Murto, which I personally thank for joining us. As usual, the format is a 60-minute presentation with panelists asking questions if they feel like. If any of you also feels like they need to ask a question that cannot be handled by the chat, do it. But of course, I would ask you to consider the option of using the chat. We're also going to have a 15-minute session for question and discussion. Please remember to keep your microphone muted during the talk. And of course, I'll remind you there is this Q&A session at the end where you can ask questions live. The talk is recorded. And before I hand over to Chiara, I want to remind you that we have these seminars every week on Thursday at 4 p.m. UK time. However, we are taking a rather long break also because of the job market. So we'll start again on February 18, Thursday, February 18, where Marco Taviani from Bocconi will talk to us about grant making. All the details on our website, or you can follow us on Twitter. And thank you, Chiara. The microphone is yours.
Thank you. So thank you very much to the organizers. Thank you for this opportunity to present this work with Doruk. So let me start from a somewhat general introduction. The war of attrition paradigm has been used to model several economic phenomena. Among these, starting at least from the 80s, it has been used to study exit from a declining industry. So when we think about an asymmetric war of attrition, what we have in mind usually is that the stronger firm can force the weaker firm to exit first. The vast majority of the literature has identified a firm's strength in the war of attrition with its profit flow. So a firm is stronger if its operating cost is lower or if the revenues are larger. So, however, the empirical literature has shown that the relationship between likelihood of survival and size of a firm are not actually do not necessarily predict that a larger firm is more likely to survive in an industry decline. Specifically, they actually have to do with the technological conditions of the industry and the industry life cycle. So what our model does is to provide a novel explanation for why sometimes a larger firm is less likely to survive the decline of the industry. Okay, so now let me be a little bit more specific. What our model does is to study a declining industry as a war of attrition with private learning. The twist is that over time, firms are going to learn about the underlying conditions of the industry. And so naturally then, the type of information that the firm has, that the two firms will have, are going to be correlated in contrast to the case in which the private information is independent. And within this framework, we're going to investigate which is the dynamics generated by interdependent private information. Again, in contrast to the standard case of independent private information. We are going to be able to provide condition for equilibrium uniqueness. In fact, our equilibrium will be unique in a strong sense. It's going to be the unique strategy profile that survives iterative deletion of conditionally dominated strategy. And in a sense, we're going to be able to tie the primitives of the industry to the predictions in terms of equilibria. Specifically, we are going to show that when there is a high degree of uncertainty, that is, both firms have little information about the market condition, then the smaller firm is going to exit first with probability 1 in the unique equilibrium of the game. In contrast, we're going to show that when the larger firm has sufficiently more precise information, then it is going to be the one that exits first with probability 1 in the unique equilibrium of the game. Okay, so I now have a literature slide. However, it's a bit hard right now to understand our contribution as related to the paper I'm listing here. So for now, let me just point out one paper, and I'll come back to the literature once I have introduced the model, so it's easier to reason about these papers. Okay, so the paper I want to point out now is Food and Dirty Role. This is the seminal paper that models exit from a duopoly as a war of attrition. They actually allow also for growing industry, but also, among other things, declining industry. They do introduce private information, but their private information concern the production cost, and so is independent across firms. So in fact, they show that the firm that has the lower cost is more likely to survive. Okay, so we're going to contrast the result with theirs. I'm going to come back to this once I introduce the model, unless there are questions right now about the literature. Okay, so if there are no questions, I'll just jump right away into the model. And again, I'm going to come back to this once I'm done with the model. Okay, so time is continuous and infinite. We're going to focus on a duopoly. So each of two firms decides when to exit from the market. Exit is irreversible. At each moment in time, the market can be in either of two states, good or bad. The state describes the profitability of the industry, as will become clear later once I introduce payoffs. To model an industry decline, we assume that initially the state is good. So at time 0, the state is good. In the state irreversibly transition to bad at a time that is exponentially distributed with rate gamma. To say differently, conditional on the state being good, at each instant the state transition at this rate gamma. And let me introduce payoff. We are going to assume that as long as a firm is active, it's going to incur in a flow cost C, and each firm is going to collect lump sum revenues R from each customer. Okay. Customers are going to arrive according to a rate that depends on the prevailing state. Specifically, they are going to arrive according to a Poisson process whose intensity is higher when the state is good and is lower when the state is bad. Okay. So again, this captures the idea that at the beginning the state is good, so customers arrive at a higher rate. Eventually the state transition, the rate at which they arrive decreases. So in a duopoly, each firm serves only customers, its own customer. That is, firm I will serve customers that arrive according to the rate lambda I omega t. In contrast, where we are in a monopoly, the surviving firm, say firm I, will serve customers that arrive at a rate equal to the sum of the rate of the two firms. The idea being that the surviving firm can serve the whole market.
Hey, Chiara?
Yes, please.
Question, just a quick question on that. Is it important that that the surviving firm gets exactly all of the remaining customers, or is it just that
Perfect. Very good.
The rate is higher?
Very good. Very good. Is actually not important. That's correct. But what is important is that conditional on the state of the world, the expected profit flow is higher in a monopoly as compared to the duopoly. Right. And so it doesn't really matter that this is the way we formulate it. So in particular, you could, for example, allow for the cost of the remaining firm also to go up, because now you may say, well, you're serving more customers, your operating cost should also go up. We can do that. That's not a problem. The important assumption is that condition on the state of the world, the payoff is higher in a monopoly than in the duopoly. Thank you for the question. Okay, so now let me just summarize the payoff. Conditional on the state of the world, the expected profit flow is going to be equal to the first line if the firm J is still active. This is the expected profit flow from I is equal to the second if firm J has already exited. So we normalize the payoff from exiting to 0, and we're going to assume that firm discounts payoff at a common discount rate R. So let me tell you about information. We assume that firms do not observe the state of the world, so to speak, online. Okay? However, of course, they learn about the underlying state of the world by observing customers. We assume that the arrival of of each firm customer, it's its own private information. That is, firm I only observes its own customer and does not observe firm J customer. Exit decisions, however, are publicly observed. So naturally, the model will combine then private learning with observational learning, because the observation that the other firm has not exited yet will carry information about the customer flow of the other firm. So if it is okay, I will now just go back to the literature. Now that is somewhat easier for me to place our paper in the literature. Okay, so I have here a, of course, non-exhaustive list of papers that I have organized according to whether they exhibit payoff externality and according to whether learning is public or private. Okay, so naturally we are in this box here. I already highlight the difference with food and Bertirol. Now it should be clear that the main difference is the fact that our information is interdependent. Okay, so the model is related to papers that analyze entry or exit in the absence of payoff externality, but in the presence of private learning. And so in particular, Rosenberg, Solang, MBA, and Murto Valimaki show how to handle this kind of a game and show that there is a strategy delay, so show that Equilibria displays strategic delay. So I'll comment a little bit more later, maybe about the connection with the Rosenberg, Solang, MBA. It turns out that in our model, because the underlying state of the words evolves over time, the technique of decomposition of belief introduced by these papers cannot be applied. And in terms of motivation, the paper is closely related to the papers by Gemart and Nailbuff and Murto. These are papers that study exit from a declining industry, respectively deterministically and stochastically declining industry. In particular, Murto 2004 studies exits from a stochastically declining industry when firms publicly learn about the underlying state of the world. The main takeaway is that in that setup, the firm is more likely to survive the industry decline if it has a higher profit flow. And so again, going back to what I said at the very beginning, these papers identify the strength of a firm with the expected profit flow. We're going to show that that is not the only thing that matters in our model. Okay, so if there are no other questions, I'll continue and conclude the presentation of the model. So let me just introduce a few parametric assumptions. So for the talk, I will focus on the case in which customers only arrive when the state is good, but do not arrive when the state is bad. So in the bandit terminology, this is a case of conclusive good news. And in the paper, we're actually able to generalize it to the case of inconclusive good news. We're going to, our results are going to mainly concern a setup in which firms are asymmetric. So this is why I'm assuming that the two rates are different. So let me conclude the presentation of the model by talking about strategies. In this setup, strategy are simply stopping time, adapting to the information available to the firm. Specifically, the information available to firm I at each point in time is described by the process of customers, let me denote that process with an IT, and by whether and when firm J has exited. Okay. And then given a pair of stopping time, the expected payoff simply takes this form. And again, this indicator function captures the fact that when the opponent exits, you will collect also its customers. We're going to study perfect Bayesian equilibrium of this timing game. Okay, so let me make a remark about strategies. So when firm J exits, say firm J exits at some time t, firm I will update its belief about the underlying state of the world and will then face a simple optimal stopping problem, because of course firm J cannot come back, exit is irreversible. So for this reason, in the remainder of the talk, I'll just describe strategy by describing the behavior along the history with no exit. Okay, I'm not going to describe what a firm will do upon exit of the opponent. Now, in principle, I should also discuss what are the beliefs following an off-the-path exit. It turns out that in our model, because the payoff that you collect upon exit is independent from the continuation behavior of your opponent, this belief play no role, and so I'm not just even going to talk about that. But if at any point someone is confused about that, I'm happy to answer any question. Okay, so here's the roadmap for the talk, even though I believe I will also only get to point 4. So I'm gonna start with a benchmark. It's going to be a public learning benchmark. So this is a benchmark in which both firms observe each other customers, just so that we have an idea of what would happen in that case, and so that I can contrast that to what happens in our model. I'll then go to the equilibrium analysis, starting from first analyzing a specific best reply problem, and then constructing the first equilibrium, and eventually proving that it is the unique one under specific conditions. Okay. So I'll go first with the public learning benchmark. So again, this is a benchmark in which each firm observes each other customer. The result is that in that case, there always exists an equilibrium in which the firm that has the higher arrival rate never exits before the other firm. Okay, so in the way I formulate here, I'm saying if firm 2 has a higher arrival rate of customers, then it will never exit before firm 1. That is, in equilibrium, in this equilibrium, firm 1 will exit first with probability 1. Okay? So the result is in line with the paper I mentioned before by Pauli. In that paper, whenever the game has a unique Markov equilibrium, is the larger firm that forces the weaker firm to exit first. Okay, and again, the idea is that the strength in a war of attrition is monotone in the profit flow that in our model is perfectly correlated with the rate of arrival of customers. Okay,
so, Chiara,
so
but
yes, please.
You don't claim uniqueness here, or?
Correct. So I don't claim that I have uniqueness all the time, but right. But it is still true that sometimes you can prove that this is the unique Markov equilibrium. We don't have a proof in general, meaning that if you give me the parameters, I can check if there is another Markov equilibrium. Whenever there is a unique, of course, that's a unique one. But that's correct. In this case, I don't prove uniqueness. Correct. Thank you. Great. So just to make sure, because Pauli in this paper does show just provide sufficient conditions for a specific equilibrium to be a unique Markov equilibrium. Great. So now let me go back to our model, and again we're back to a setup in which customers are privately observed, and I want to analyze a very specific best reply problem. Suppose that firm J never exits first. Okay, so now that is never exits before firm I. So now the best reply problem of firm I is simple. It's a simple optimal stopping problem. The lambda J doesn't appear in this expected payoff. Firm I knows that firm J will never exit first, and so it's just going to choose its optimal strategy that we know to be a cutoff strategy. Specifically, firm I will find it optimal to exit as soon as its posterior belief about the prevailing state falls below a certain cutoff. Let me denote that cutoff with pi star lambda J. So what I'm going to do in the next slide is showing a few belief trajectories induced by this strategy profile. So again, firm J never exits, firm I exits as soon as the belief falls below a certain cutoff. Okay. So what I'm plotting here is the posterior belief of firm I. Again, a few observations in this realization, firm I is observing 3 customers and is exiting at the vertical line here, because that is the first point in time at which its posterior belief hit the cutoff belief. Okay, so of course horizontal axis is time. And so a few things to notice. First, the evolution of the belief of firm I is uniquely driven by private learning. Firm J is not supposed to exit, so the fact that firm I observes that firm J is still around brings no news whatsoever. Second, because we are focusing on the case of conclusive news, whenever a customer arrives, the belief of firm I jumps all the way to 1. Okay, specifically here, this is why I said that these are 3 customers. Okay. And last, the time elapsed since last observing a customer is a sufficient statistic for the belief of firm I at any point in time. Okay. So this means that I could have equivalently described the best reply of firm I as follows. I could have said firm I exits as soon as the time elapsed since last observing a customer exceeds a certain amount. Okay, so this is the first time that firm I hasn't observed any customer for an amount of time of length tau star lambda j. So this is this function will appear several times in the talk. I'll call it the first exit time. So the first lemma concerns this first exit time. The first exit time is positive only if the arrival rate of customer is sufficiently high. It is single peaked, and it converges to 0 as the arrival rate of customers goes to infinity. Okay, so let me just explain what the intuition. So the non-monotonicity is coming from 2 countervailing forces. On the one hand, the higher is the arrival rate of customer, the higher is the marginal benefit from remaining in the market for any given belief. In fact, the lower is the cutoff belief. On the other hand, the higher is the arrival rate of customer, the faster the firm becomes pessimistic. That is, the faster the belief decreases from 1 to any given cutoff. Okay, it turns out that these 2 forces work in such a way that the first exit time is precisely single peaked. The result generalizes one that was already observed in a framework in which the state doesn't change, doesn't evolve over time, and news are conclusive. We generalize by Halak, Karthik-Luke, and Bochef and Lee. Okay, we're going to use this fact later on to when we provide sufficient condition for equilibrium uniqueness. So let me start with a preliminary observation, and then I'll give you the first equilibrium. Okay, so a preliminary observation is that along any history we know exiting is a dominated action for firm I whenever its posterior belief about the underlying state is above the benchmark cutoff. Okay, and so that is not surprising. In fact, remember that when firm J never exits before firm I, it is optimal for firm I to remain in the market when the belief is above the benchmark cutoff. But the case in which firm J never exits first is the worst case scenario payoff-wise. The possibility of becoming a monopolist can only strengthen the incentive to remain in the market as compared to that benchmark best reply problem. Okay, so that's in a sense a simple observation. Okay, so I'm gonna refer to this observation later on in the proof. So now let me give you the first equilibrium, and then I'll try and convince you that that's actually an equilibrium. So to do that, I need 2 pieces of notation. First, let me define sigma theta to be the strategy of a firm that prescribes exiting as soon as no customer has been observed by for an interval of time of length tau. Okay, so again, that is to say, in other words, according to the strategy sigma tau, I guess I said theta, sigma tau, the firm exits at time t if it has observed no customers in the interval t minus tau t. So let me define with the sigma infinity the strategy that prescribes never exiting before the other firm. Okay, so here is our first equilibrium. If the first exit time of firm 1 is larger than the first exit time of firm 2, then there is an equilibrium in which firm 1 never exits first and firm 2 adopts the cutoff, adopts the best reply that we have analyzed in the previous slides. Okay? So again, in this equilibrium, firm 2 exits first with probability 1. Okay. Now, by construction, the strategy that firm 2 is using is the best reply to what firm 1 is doing. That's the way I derived that tau star lambda 2J. Now, let me try and convince you that the strategy that firm 1 is using is actually a best reply to what firm 2 is doing. Okay, I'll try to do that in a series of pictures in the next slide. So first, I want to choose parameters so that this premise holds. Okay, so here is my choice of parameter. So this is the first exit time for firm 2. This is the first exit time for firm 1. Okay, I get them by looking at when is the first time the belief hits the cutoff belief if based only on private learning on the history in which no customer arrives. Okay, let me now plot a possible belief trajectories given my candidate equilibrium. Again, firm 1 adopts the strategy of never exiting first, and firm 2 adopts the benchmark best reply. So in this illustration, again, firm 2 observes 1, 2, 3 customers and exits at the vertical line here. Okay? So given the strategy adopted by firm 1, the belief of firm 2 is uniquely driven by private learning. Now, let me reason about the evolution of the belief of firm 1. So first of all, before the time tau star lambda 2G, that's the first exit time of firm 2, the belief of firm 1 is uniquely driven by private learning. Firm 2 is not supposed to exit before that time, and observing that it has not exited yet brings no news. Now, ex ante, there is a strictly positive probability that firm 2 exits at the first exit time. For this reason, at that time, the belief of firm 1 jumps up along the history in which firm 2 does not exit. For now, let me not explain why the belief is constant afterward. I'll come back to it in a second. Let me go to this point in time, 2.5. At that point in time, firm 1 observes a customer. The belief jumps all the way to 1. And then it decreases again. Again, it decreases because firm 1 is not observing customers. And on the other hand, is decreasing at a lower rate as compared to the beginning of the game, because the good news from observing that firm 2 has not exited yet dampens the bad news from the absence of customers. Okay. Notice that the belief eventually plateaus. Now I want to try and explain why that is the case. So
just a clarifying question: does it plateau or does it asymptotically approach that level?
No, actually, no, it's not asymptotic, meaning that at this point, precisely at 2.5 plus tau star, and from any point afterwards, the belief is exactly constant. It's not like the derivative is going to, it's precisely constant. Now I'll try and explain you why, okay? And in fact, is equal to this plateau here, is the same, okay? So let me try and explain why. So now let's consider the inference problem at the right edge of the gray area, the inference problem of firm 1, okay? At that point in time, firm 1 hasn't observed customers for an amount of time that is greater than than tau star lambda 2J. In fact, hasn't observed customer since 2.5, okay? However, firm 1 knows that firm 2 must have observed a customer at some point in the gray area, for otherwise firm 2 would have exited. In fact, the strategy of firm 2 prescribes exiting as soon as no customer being observed for an interval of time of length tau star lambda 2J. As a consequence, firm 1 infers that the state must have been good at the left edge of the gray area. Again, if firm 2 has observed some customer in the gray area, it is because the state was good at this left edge. Okay? As a result, the absence of customer, the absence of firm 1's customer from 2.5 to the left edge of the gray area is irrelevant in terms of inference, is not useful information at all, because after all, the state was good at this point. To say differently, the kind of the inference problem of firm 1 at this point in time, again to the right edge of the gray area, is precisely identical to the inference problem at 2.5 plus tau star lambda 2G. Is firm 1 is combining two pieces of information: the fact that itself it doesn't observe any customer for an amount of time of length tau star lambda 2G, and firm 2 must have observed at least one customer in the last amount of time of length tau star lambda 2G. Okay, so that's why it's precisely constant. Hopefully that's clear. So this is in fact the same reason why here it is also precisely constant. Great. Okay. So yes, please.
So this, this requires this conclusive news.
Correct. That's a great observation. This is true only in the case of conclusive news. That is correct. And so this is why in the case of inconclusive news, you need, the argument requires a little bit more work. And in fact, it turns out that all the arguments I'm going to present in the talk is mostly going to rely on this assumption of conclusive news. I'm going to point out what's the challenge with inconclusive, but that's definitely true.
Can you derive the belief evolution in that case? How does it look like?
You mean in the case of inconclusive news?
Yeah.
Mm-hmm. Okay, so very good. I think I took out the picture from here. Okay, so now what I did, okay, very good. So in that case, in the case of inconclusive news, I actually, so what we did is you can actually, you cannot write down, or at least we couldn't write down a nice formulation of the belief. What we did is if you simulate it, you see that actually it is, so not only you see it simulated, but in the simulation you would see that still it is asymptotically, it is going to be asymptotically constant. However, we actually then prove it. Then I'll tell you later how you can actually, you need to actually, what is actually that you need to prove in that case in order to prove that this is an equilibrium. Okay, so well, maybe I can just anticipate it now. So let me conclude this observation and then I'll go back to the inconclusive. So just to be sure, this observation, the fact that the belief of firm 1 never goes below a certain level, implies that firm 1 finds it dominant to remain in the market at any point in time. And so again, this means that never exiting first is the best reply for firm 1. Okay, now let me go back for a second to the inconclusive news case. Okay, in that case, what we can show is that if, let me just think for a second. Great. If firm 2, so this statement only required that the first exit time of firm 2 was before the first exit time of firm 1. Okay. So instead, in the case of inconclusive news, what we can show is that the results holds provided that the arrival rate of customer of firm 2 is sufficiently high. So the reason being that at that point, the problem of firm 1 is that firm 1 is trying to learn from firm 2 about the underlying state of the world. If firm 2 is learning from information that is arbitrarily precise, even if it's inconclusive, that doesn't really matter. In the limit as lambda 2G goes to infinity, I still only effectively, in the limit, I only rely on observational learning because my news is bad enough as compared to the other firm news. And as a result, again, you get that the belief is bounded away from the single agent cutoff. Okay, so that's a bit, I think I wasn't too clear, but that's the idea. Okay.
Great. So let's see. I find a couple of things striking about this. So one is that these constant intervals don't use any symmetry between the two lambdas. So it's like the offsetting force. It doesn't depend on the other player's lambda.
No, it does actually. Okay.
Oh, it does.
So it does, meaning that you see that if you think about firm 1. Okay. Here, firm 1 observes the last customer at 2.5. When is the point in time, the calendar time at which the firm 1 beliefs becomes constant is 2.5 plus tau star lambda 2G. because that is the moment in time at which I start discarding some of my private history because I just know that, well, the state must have been good at that point because the other guy is still around. So you see what I mean? Depends.
I see.
In
so
here.
The time at which, but the fact that it's able to completely offset it doesn't depend on like the symmetry of it.
That's correct. Very good. That is true. Exactly. That is correct. On the other hand, I believe that where this plateau is, the position does depend also on lambda 2G, but the fact that it's above the cutoff of firm 1 does not depend. Is above regardless of how big is lambda 2G. I hope that addressed the question.
Yeah. Thanks.
Thank you. That's a great observation. Okay, great. Should speed up a bit. There is an easy corollary, and this is the following. If firm 2 learns sufficiently fast or the rate of arrival is sufficiently large, then there is an equilibrium in which firm 2 exits first with probability 1. And as I said, probably this is the result we also have in the case of inconclusive news. Great. Let me now go to the main result. The main result concerns equilibrium uniqueness and goes as follows. First, we show that for any rate of arrival of firm 1, provided that the rate of arrival of firm 2 is sufficiently high, in the unique equilibrium, firm 2 exits first with probability 1. Okay. Second, second, we show that there exists an open set of pairs, lambda 1G, lambda 2G, such that firm 2 rate of arrival is smaller than firm 1 rate of arrival, and yet in the unique equilibrium, firm 2 exits first with probability 1, provided that the revenue, the discount factor, and the transition rate are high enough. Okay, so what I'm saying is that in both of this setup, we are providing sufficient condition for this one to be the unique equilibrium. So this is the strategy profile according to which firm 1 never exits first, and firm 2 adopts the time-independent cutoff tau star lambda 2J. But with the difference that in part A, firm 2 is, so to speak, the large firm. In the second, firm 2 is, so to speak, the small firm. What I'm going to do now is I'm going to try and show the main ideas of the proof of part A. Then, if I have time, I'm going to highlight what are the challenges in generalizing that proof to part B, and that will hopefully clarify why part B is weaker, meaning we need to play with parameters in order to guarantee uniqueness. Okay, so again, the proof is going to go through several steps. You're going to see again pictures very similar to what you have seen so far. Okay, so the proof relies on iterated deletion of conditionally dominated strategy as defined by Shimorji and Watson. Strictly speaking, Shimorji and Watson define iterated deletion of conditionally dominated strategy for complete information extensive form game. Our game is not a game of complete information. We are going to say that a strategy sigma is dominated at some information set if there is another strategy sigma prime that differ from sigma in successor of this information set, and such that for any strategy of the opponent, together with a system of belief consistent with this strategy, the strategy sigma prime yields a strictly higher payoff than the strategy sigma. Okay, it should be clear enough during as I explained the proof. So first, let me assume that twice the first exit time of firm 2 is smaller than the first exit time of firm 1. We know that the first exit time is single peaked, so provided that lambda 2G is high enough, this inequality holds. Okay. So second, let me recall that along any history we know exiting is a dominating strategy when the posterior belief about the prevailing state is above the benchmark cutoff. Okay, so this allows us to already delete some strategies. Now we are in fact going to claim the following. If the rate of arrival of firm 2 is sufficiently high, exiting before its first exit time is a conditionally dominated strategy for firm 1. Okay, let me just highlight the challenges in proving this claim. The claim would be obvious if the claim is obvious whenever firm 2 is using a cutoff strategy. If firm 2 uses a cutoff strategy, observing that firms 2 remain in the market always bring good news. So of course, the belief can never fall below the cutoff before that time. However, we need to prove this for any strategy that has survived the first round of deletion, not only for cutoff strategies. It turns out that is true, provided that the rate of arrival of firm 2 is sufficiently high. So now, once we know that, let me proceed in our iterated deletion. Let me consider an history of length 2000 lambda 2g, twice the first exit time of firm 2, along which firm 2 has a posterior belief about the prevailing state equal to the benchmark cutoff. Okay, let me show this an example of such a history in this picture. So again, I chosen parameters such that the first exit time of firm 1 is greater than twice the first exit time of firm 2. If firm 2 at this point in time has a belief equal to the cutoff belief, it must be the case that the last customer was observed at tau star lambda 2g. Okay, so and again, the first claim I show you says that firm 1 will find it dominant to stay for any point in time before tau star lambda 1g. I now argue that if the rate of arrival of firm 2 is sufficiently high, along this history, exiting at this point in time is a conditionally dominant strategy. Okay. So again, this is what I just said in words. If the rate of arrival of firm 2 is sufficiently high, along this history, exiting is a conditionally dominant action for firm 2. Okay. I prove that by providing a bound on the continuation payoff of firm 2 at that point in time. I show that the bound is negative, so exiting is dominant. Okay, so the continuation payoff, if firm 2 were to stay, would be bounded above by the following. Let me take it piece by piece. So first, let me describe the hypothetical scenario that gives me the bound. The hypothetical scenario is a scenario in which firm 1 is exiting for sure at time tau star lambda 1g. At that point in time, on top of that, firm 2 is told the state of the world, and the state of the world never transition to bad ever after. Okay, so that's clearly an upper bound. So the first term captures the payoff that firm 2 would collect from time 2 tau star lambda 2g up to the first exit time of firm 1. We know that is negative by the definition of the cutoff belief. This is the continuation payoff after tau star lambda 1g. It comes, so as I said, at that point, I'm assuming that firm 2 is told the state of the world at that point. So if the state is bad at that point, that happens with complementary probability then it just exits, because state is bad, you would only get loss. If the state is good, let's just assume that the states never transition to bad ever after. So we have an upper bound on the continuation payoff. Okay. Turns out that if lambda 2g is high enough, this sum is actually negative. We know that the first term is negative. Let me just highlight why the second is negative. If the rate of arrival is high enough, the benchmark cutoff is arbitrarily close to 0. And on top of that, one can show that this even multiplied by the rate of arrival customer is also going to 0. The idea is that firm 2 is already very pessimistic. It doesn't even want to stay another split second because the gain is anyway small, given that even if firm 1 were to exit, the state would be bad anyway with large probability. Okay, so this tells us that then at time 2 tau star lambda 2g, firm 2 would find it dominant to exit whenever the belief is below the benchmark cutoff. But then, if firm 2 does not exit, firm 1 would infer that firm 2 posterior belief must have been larger than the benchmark cutoff. This gives us a lower bound on firm 1 belief at that point in time, along any history with no exit. Okay, so I claim that this is the lower bound it gives us. It's not obvious; it needs a little bit of an argument, but let's take it as it is for now. Having a lower bound on the belief of firm 1 allows us also to provide a bound on the first time when exiting would not be a dominated action for firm 1. In fact, along an history in which firm 2 does not exit by that point in time, by 2 tau star lambda 2g, exiting before tau star lambda 2g plus tau star 1g is a conditionally dominated action for firm 1. This requires the very same claim I gave before, the fact that firm 2 being still around roughly gives good news in this framework, provided that firm 2 learns sufficiently fast. And so we now know that firm 1 will never exit before that point in time. Okay, so here is what is telling us. So now let me do a last step in the step-by-step construction. Let's again put ourselves at some point, at point now 3 tau star lambda 2G, and consider the history of that length along which firm 2 has a posterior belief about the prevailing state equal to the cutoff belief. Notice that the continuation game and the surviving strategies looking forward are precisely the same as those that firm 2 was facing when I was considering the problem at 2 tau star lambda 2G. Okay, let me say differently. From the point of view of firm 2, looking forward, the problem looks exactly the same as the problem we consider at 2 tau star lambda 2G. But we already proved that at 2 tau star lambda 2G was dominant to exit, and now again, it is dominant to exit for firm 2 whenever its posterior belief is below the benchmark cutoff. Okay, so this is again the representation of the fact that looking forward, the problem is precisely the same as the one we were looking at before. It turns out that the logic clearly can apply recursively, so to allows us to conclude that indeed in the unique equilibrium firm 2 exits first with probability 1. Okay, so again, let me just point out that, I mean, a priori, this is not a stationary game, but what we develop is a recursive argument that allows us to carry over arbitrary many rounds of deletion and to conclude that we have a unique equilibrium. Okay, so let me now just explain. If there are questions, you should feel free to ask. Let me just highlight. Yes, please.
Okay, let me. So it's very nice how you proceed by this elimination process. Just to understand, the way how I would approach this problem is that I would just look at these two different possibilities for equilibrium, where one of the firms just decides to stay forever and the other firm best responds to that. So I would take all possible parameter combinations and just see where a particular simple poor strategy candidate is an equilibrium. So firm 1 stays forever, firm 2 best response, and then the vice versa. And I guess there would be an intersection of regions where both would be an equilibrium. So my question is, do we get the same result? Does that lead to, I understand that I'm missing some other possibilities for equilibrium by doing this.
Exactly. So let me, okay, so very good. So let me just see if I understand correctly, okay? So what you're saying is that, well, first of all, why don't you do this? You first just check, and you correctly guess that sometimes both of these could be equilibrium of the game, not surprisingly.
Yeah.
If the game is sufficiently symmetric, we both have an equilibrium in which firm 1 exits first, and we have an equilibrium in which firm 2 exits first. On top of that, there are mixed equilibria. We construct at least one just to make the point that they exist.
Yeah,
okay?
So basically I'm just asking whether this whole thing boils down to checking when these equilibria go.
So actually, there are more subtleties to be taken care of. Let me see how I can put it. Okay. Okay, so let me say it differently. Let me see if I can. If you only check whether these and these are equilibrium, it might as well be that you end up with this being an equilibrium, but that still doesn't prove that there are no other equilibria. In particular, just to point out the challenges, I'm not sure this addressed your question, but notice that in this game, we're actually not even able to prove that all games are in cutoff strategies. Okay.
Yes, I completely understand.
right? So the reason is that we have payoff externalities, so it's not, like Rosenberg, Solang, and VA proved that we can't. And so, in fact, we know very little on the whole set of equilibria. Okay.
Yeah, that's why actually basically all I'm doing is asking whether there is a difference.
And so so now, the problem is that because I know so little, I actually cannot tell you, oh, you know what, you're forgetting these other equilibria if you do that. Well, I know there is a mixed strategy equilibrium, but the one I have is very simple. I actually don't know much more other than that, right? So, and so in fact, I wish I were able to more cleanly show a non-cutoff equilibrium, because it doesn't necessarily, it may as well exist, but I actually don't know.
Okay.
Yeah, sorry, this is not the best answer.
It's okay.
But there are still things to be, let's say, taken care of besides checking existence of these two. Okay, so let me just highlight quickly the challenges with proving that for part B, and then I'll talk a little bit about how we can generalize the result in some comparisons. Okay, so notice that part B identifies sufficient conditions for having an equilibrium in which the smaller firm exits first with probability 1. Okay, so now the challenges come mostly in two places. Effectively, I had a claim that I was describing as saying that for firm 1, observing that firm 2 is still around brings good news, regardless of which strategy firm 2 is using among those that have survived all all rounds of deletion so far. The problem is that now firm 2 is the small one, so it conveys a weak signal anyway, and there are still too many strategies. The first round of deletion has little bite in that case, so that's one of the challenges. And so the other challenge is showing that that firm 2 finds it dominant to exit at any round and tau star lambda 2g. Remember that when I show you that that bound on the belief on the continuation payoff, sorry, I was using the fact that the benchmark cutoff is converging to 0 as lambda 2g goes to infinity, but now that's bounded away from 0, so that cannot be used anymore. So these are the reasons why actually part B is weaker. We need to be able to play with the other parameters in order to show equilibrium uniqueness. So so now let me just say the takeaway, like more informally. We say that a firm as a signaling disadvantage is the first exit time is smaller than the opponent's first exit time. And we've seen that if these first exit time are sufficiently far apart, in the unique equilibrium is firm I the one that exits first with probability 1. Okay, and so in a sense, we could say that private learning generates what we call a discouragement effect, as opposed to what we usually call encouragement effect in strategic experimentation model. So firm I would be willing to stay in the market at a belief lower than the benchmark cutoff if only if it's expected to eventually become a monopolist. However, staying in the market makes the opponent more optimistic, sends a signal against its own interest, and delays the exit of firm I, anticipating a longer duopoly. Then firm I is just discouraged from remaining in the market at that belief and just will exit at a single prayer cutoff. Okay? So there is another way of putting the same result, and I should have mentioned it earlier. So I said that the earlier literature identifies the strength of a firm with the expected profit flow. What we show is that now also what matters are also the signaling consequences of a firm action. And so it is not true anymore that strength is monotone in the expected profit flow, going back precisely to the monotonicity of the first exit time. So in terms of prediction, our model predicts that if none of the firm has very precise information, then it's going to be the smaller firm that exits first. To the opposite, when the large firm has sufficiently precise information, then it's going to be the small firm that survives the industry decline. Okay, so these are more of a stretch. These are just drawing from the from looking at how our set of pairs that guarantee equilibrium uniqueness look like. So as anticipated, it's not surprisingly that if the game is sufficiently symmetric, both strategy profile, we both have an equilibrium in which firm 1 never exits first and an equilibrium in which firm 2 never exits first, and mixed strategy equilibria exist. Let me just say a little bit to what extent we can generalize to the case of inconclusive news. As I said before, there is we can generalize some of our results. In particular, we can generalize theorem A. Okay, that is, we can show again. So in this case, I'm going to normalize the rate of arrival of customer in the best state to be equal to across the two firms. And we are going to be able to show that for any arrival rate in the best state and any arrival rate of customer for firm 1 in the good state, provided that the arrival rate of firm 2 is sufficiently high, in the unique equilibrium, firm 2 exits first with probability 1. Okay, and now let me just give you the somewhat hand-waving intuition of this.
Chiara,
So
you have 5 minutes.
Yes, thank you. So intuitively, the idea is that in the limit, as firm 2 arrival rate goes to infinity, firm 1 is going to base its inference mostly on observational learning. And so in the limit, the fact that it learns via inconclusive bad news instead of conclusive bad news becomes irrelevant. Okay, let me add one point that address what Pauli was asking before. So if you think about it, so it's going to be a little bit hand-waving, but I'll do it anyway. So as I shown, the results so far rely on the conclusive news assumption. So in particular, I was saying that whenever that the belief is precisely constant, because I would infer from observing that firm 2 is still around, that say the state was that the state was good actually, an amount of time of length tau star lambda 2g ago. Okay, now in this case that's not true anymore. The fact that firm 2 is still around doesn't tell me that for sure with probability 1 the state was good in that moment in time in the past. Yet because firm 2 learns very fast, that's still arbitrarily likely. These are still arbitrarily likely that the state was good just up to a second ago, because for otherwise this firm would have exited. It takes just a split second with no customer for this firm to exit anyway. And so in that sense, you still get that the belief is gonna be asymptotically constant. Okay, so that's a bit of hand-waving, but hopefully it's helpful. So there are some natural extension. It's easy to introduce asymmetries in other parameters and some form of public news. And so actually the results go through in that case. And there is also a very simple comparative statics that is the following. So if you fix a set of asymmetric parameters, so now I'm taking cost, revenues, and discount factor to be asymmetric, then the set of pairs that we have identified in the theorem is going to be increasing, meaning it's becoming bigger, as I increase the cost, the operating cost, and the discount rate of firm 2. So that's not surprising. Think about where these two terms appear. Mostly the key role, they were playing the key role in that bound I was providing. And so if I now make firm 2 more impatient or the operating cost higher, definitely wants to exit. So in that sense, it is an easy comparative static to prove. So we actually believe that it would hold true even if I were to set the discount factors to be equal to each other in that comparative static, but we were not able to show it. So now I'm going to jump to the conclusion. So I'm skipping is a part that talks about the fact that our model can also deliver some insights in an entry model. This is strictly speaking is an exit model, but let me skip this for now and I'll just jump to the conclusion so I stay in time. So so what we've done in this paper, we develop a world of attrition model with private information, and we provide a sufficient condition for equilibrium uniqueness. I didn't really point it out, but clearly our proof circumvents the computational higher order belief. That is something that is quite hard to do in our setup. So this is something Aaron knows well about, of how hard it is to compute higher order belief. And so we hope that this idea of just providing bounds on the belief is applicable to other setup with private learning or private monitoring. So so clearly the model is very stylized, is an exit model, but it doesn't incorporate any pricing decision. That's definitely would open the door to other ways of signaling. And actually, we haven't investigated much the comparative statistics in terms of profit. Okay, so I'll conclude in time, and thank you very much. So I'm happy to take any questions.
Okay. I don't think there was a question in the chat, but I think that's been dealt with. So maybe Paolo.
Should I look at it?
Yes, Daruk answered that question.
Okay.
But
yeah.
maybe we can
okay,
start with Paolo or Aaron, whichever of you wants to go first.
Sure. So actually, this future directions partly stole what I was going to ask about, but so in thinking about how a firm might respond to this signaling disadvantage, it seems like you might get some perverse implications, like, do I want to slow down my customers? And I guess one way you could do that is through higher prices, and you might get higher, higher revenues both through the higher prices, but also by slowing down the arrival rate and this signaling disadvantage. But do you have any preliminary thoughts about that? Or
very good, very good. Okay, so I think that's an excellent question, and even a let's say even a simpler way to try and start tackling such a question, from my point of view, would be saying, okay, now what if at the beginning you can choose which is your rate of arrival? What do you want? Right? So because you know that now if you choose a higher rate of arrival, then that comes with benefit and cost. Okay, so this is why indeed, if I were to know a little bit better about comparative statistics with respect to profit, I could tell you something. Because if you, to the extreme, if my rate of arrival is very high, it's true that I'm going to be the one that exits. But anyway, I exit when the state is bad because I learn so fast. So there's little to lose anyway. Right, so it's not totally obvious, even just this simple comparison. So actually, I don't know. And on top of that, it is true that it would be interesting to think about now once you incorporate either pricing decision or you think more generally competition a la Cournot, but then somewhat, your capacity affects the speed of learning or something. And so that's definitely something interesting. I must say, as you see, I'm speculating. I have no idea how that would go, and so I actually don't know much. But I do think that there is, avenues for new research there. Yeah.
So let me then ask you your views about different news processes. So I guess one open problem actually is that to think about a model like this, where there is private learning, but the learning is through Brownian motion type of signal. And I guess the difficulty is that you have this higher order beliefs right away, even if there's no state transition. So I was wondering if your method, this elimination of dominated strategies, would actually give some mileage.
Okay, so I think the question is not totally open because I think Aaron has been closing it, that open question. So studying, private learning with Brownian.
I should have a look.
So actually though, but I don't, so that's a good question, and design is not clear. So that's what we would like to try and think, whether you can use the bounds to think about dealing with that kind of, correct. Let me just think for a second. Yes, so at least even just correct, because at least if I could even just assume, so even just focusing on cutoff strategies, suppose you somewhat use cutoff strategies in your private belief, so then that should already be helpful because at least I see you're around, so your private belief should be above some cutoff strategies. So yeah, it's something that we should try and think about. That's a very good point. Yes, thank you. Yeah.
And Chiara, it seems like you're actually taking two steps of contribution, it seems. So in the paper, you mentioned that you could have just ex-ante realization of G or B, but then it's constant throughout time. And so there, it seems that the first order belief would perhaps capture the second order belief. But
no, I need you to restate. Can you restate this?
Okay.
I didn't.
Right.
I couldn't follow.
A simpler model would be G or B is realized at the beginning of the game randomly, and then it's constant forever. And when you have a changing state, you have these correlated private signals. And so the higher order.
Very good. Very good. Very good. Thank you. Yes.
But it seems like, already an interesting contribution perhaps in the simpler model. In that simpler model, do you have second order beliefs on top of the first order beliefs, or the first order belief is a sufficient statistic for the second order belief?
Perfect. Okay, great. So what you're suggesting is, let's consider a case in which the state of the world realizes time zero in transition. Is that correct? Yeah. And you're saying is that model a tractable model? Is that model identical to? Correct.
I would also be curious just to understand what would be the difference in results in that more simple model as compared to this. So what
very
do we
good,
gain
very good,
by
very
this?
good, very good, very good, very good. Okay, great. So let me just think about it. Okay, so the difference in result would be the following. Suppose the state of the world is realized at time zero, and that's it. So so then a firm would exit. So there would be a point. So then if you think about the best reply problem, it would be easier, meaning you would exit at this point you would exit as soon as your belief goes below a cutoff. But if you don't exit at that point in time, you're never going to exit ever after, because if you don't exit, it's because you observe a customer. The state is good, is going to be good of ever after. Okay, so in that sense, it's closer to, in that sense, there would not be continued revelation of information as time goes by, meaning the observational learning is just going to occur at one point in time, and then that's it, I believe. So if, I'm thinking a model in which if the state is good, there is space for both. If the state is bad, there is only space for a monopoly, okay? And so that would be, I think that would be what you would get. And in that setup, one may analyze a symmetric game, and I do believe that there are papers doing this. So that's, I think, would be the dynamics. Would it still hold true?
But in terms of the uniqueness results that are the main focus of it.
Right, very good. That's a good point. I do believe, yeah, I think it could be that yes. So yes, I need to check that. I'm not sure. I would guess it would hold anyway. That's correct. Yes. So in a sense, now I'm taking a little bit of a wild guess, but I think the result would generate, meaning not generate, but it would the result would be true. We would have sufficient, we still have, all that matters is that first exit time. We know that the first exit time will still be single peaked. In fact, that has been shown in previous paper, and indeed you would get these two asymmetric equilibria, and I believe they would be unique provided that the setup is sufficiently asymmetric. Yes, correct. Yes. So in that case, right. So the learning dynamic would be somewhat simpler, but yes. So the main takeaway, I think would still be there, right? So, and as Aaron tried to point out, in fact, our challenge is also that because instead we're assuming that the state is transitioning at some unknown time, it is more challenging to think about decomposite private belief and public belief, because in a situation in which the state realizes at time zero, and then we just get private signals, then our signals are conditionally independent, conditional on the state that has realized at time zero. Instead, in our model, the underlying stochasticity is richer because it concerns the time at which the state transition. Specifically, conditional on the state being bad today, our signals are not independent, they are correlated. Because the last time when we saw a customer has to do with when the state transitions. So that's that I think why it simplifies. But yeah, that's still a benchmark I should have better in mind. Thank you for pointing it out.
Okay. Does anybody want to ask a question?
Could I ask a question?
Yes.
Hi. Thanks very much for the very nice presentation. I was thinking, is there room for some information acquisition? So let's say that I'm the high arrival rate firm, and I can pay a small cost to observe the lower one. Would that be? Would that bring us back to the public information?
Right. So yeah, as I anticipated before, to area is not obvious, meaning that because in this setup, it's not obvious whether so on the margin, it's not obvious whether you are better off or worse off having more or less information. Because again, in our model, information comes together with more customers. So then that's true. On the other hand, if instead you were to think like about only information, yeah?
I observe just the other players' arrivals, right?
Okay, perfect. Very good. It seems that in our model, there is a sense in which the firm that adopts the strategy of never exiting first is hiding behind its own ignorance. So it's not obvious whether you would like to, say, commit to observe the other guy customers. Think about the case in which in our model, the small firm never exits first. Instead, we show that in the case of public learning, there always exists an equilibrium in which is the smaller firm that exits first. And so this means that in this case, the smaller firm would rather not observe the customer of the other. So that's okay. Yeah. So that's actually not obvious. So yeah, I have to think about that.
Thank you.
Okay, thank you. Anybody else?
I have a question.
Miguel.
Yeah. Yes. So I'm trying to think of the case in which the large firm has perfect information about the state of the world. I guess that corresponds to lambda going to infinity.
To the limit.
I getting it right? And then in that case, basically what happens seems pretty, I'm not sure whether it is obvious, but it seems that, I mean, the large firm is going to learn immediately the state of the world, and then it's not surprising that it's the first one in leaving the market, right? Am I getting it right?
That's correct. That is correct. But notice, however, that in our model, the large firm also has an arbitrary large flow payoff from remaining in the market. Yeah, so in principle, it should be the one that can endure a duopoly longer, right? So the existing papers would say that whoever has a higher profit flow can endure a monopoly longer, and so it's going to force the other firm to exit first. But that's definitely true. That's the reasoning in the limit. That's correct.
Yeah, but I see. But under the assumption that even the large firm doesn't find it profitable to remain in the market as a monopoly,
actually, though, we can. Okay, very good. In the case of inconclusive news, we can though actually relax that assumption. So because now when I have incomplete news, inconclusive news, I would also have rate of arrival, positive rate of arrival customer in the bad case, in the bad state. And indeed, we can also generalize it to that case. Okay, so it holds anyway. So it's true that it's a matter of two forces, and which is the strongest. And as you point out, in the limit, which is the stronger one is the information, let's say the signaling force, but that's still to be proved. Yeah.
But it also hinges on the fact that it is the profits of being a monopoly are the same to both firms.
Very good. Oh, I missed that. Sorry. Okay. Very good. Very good. Very good.
Yeah, because
let me think if it hinges on that though. No, actually, it does not hinges on that.
At least in the limit with perfect information, no? Otherwise, the firm with perfect information. I'm not sure. Okay.
No, so there is okay. So let me just take so now just to be sure, it doesn't hinge on the fact that condition on the bad state you don't want to be a monopolist. In fact, we can allow for that case. On top of that, in the proof, there's nowhere that you saw the behavior upon becoming a monopolist. The whole thing, the only thing you saw was the time, what was the behavior conditioned on the history in which nobody exits. So this is in fact in contrast to Pauli's paper that instead is important what's happening, like it's more play more a role, your cutoff in the monopoly. In here, actually, what's happening upon we are in monopoly doesn't really matter.
So
I hope that answers the question.
Can I comment quickly on?
Please,
on this?
yeah.
So I think thinking about what's the sort of economic contribution in your paper, I see it as pointing out that there is this informational reason why actually good information can be a bad thing in this kind of a war of attrition situation. So maybe one way to highlight that a bit more would be just to think about a case where lambda times, you keep lambda times R constant, and then just increase lambda and see that actually hurts a firm.
Perfect. Okay, so this is a great point. What Pauli is suggesting is, why don't you only introduce asymmetry, if I understand correctly, asymmetry in the information, and you don't introduce asymmetry in the profit flow. So in that case, whenever the equilibrium is unique, is the firm that has the more precise information that exits first with probability 1. That's a fact. Like one can prove it because instead of single peakness, you have monotonicity of the first exit time. Now, the reason why we put them both is because we believe that the contribution is also identifying sufficient conditions for either of the two being in equilibrium, and this somewhat we think that it's bad, so it provides a better bridge between existing results and what we have here, on top of the fact that we do believe that it's reasonable to assume that a firm that has better information also has larger profits. So in that sense, we want to make sure that the two forces go in opposite direction, but it's one force that wins one time and the other that wins another time. I hope that makes sense, Pauli. Yeah,
it does, but I think it would be perhaps good still to highlight.
I see.
Think about it in isolation, this information somewhere in the paper.
Yeah, but indeed, also we did do that benchmark for ourselves, but we didn't put it in the paper. But that's definitely a good benchmark to have in mind, and that would precisely be a case as Angel, in which it's clear where the result is coming from. So we're saying, well, on top of that, it wouldn't be destroyed by the introduction of asymmetry in payoff, but that is where it's coming from.
Thank you.
Okay, can I just take a moment just to say that we are stopping the formal part of a talk here. We are going to stay on for a little bit to finish the discussion and